20 covers the chemistry of carboxylic acids and nitriles. Carboxylic acids are a functional group that contain a carbonyl as well as a hydroxyl group attached to the same carbon. A simple example of a carboxylic acid is acetic acid. Acetic acid has a methyl group attached to the carbon that has the carboxylic acid functional group. Acetic acid is a component of vinegar. Vinegar is usually a 5% or less solution of acetic acid in water. Nitriles contain a carbon to nitrogen triple bond. Simple example is the common organic solvent called acetonitrile, which has a methyl group attached to the nitrile. Carboxylic acids are one of the most widely uh, or common functional groups in nature. There are many examples. For example, formic acid, which is what ants or some ants use to defend themselves. And oleic acid is an example of a fatty acid. We're going to cover some fatty acids later on in this chapter. Oleic acid is a bile acid that is synthesized by the liver from cholesterol. So the structure is shown on this slide here, and you can see the carboxylic acid, which is highlighted. This carboxylic acid is crucial for the digestion and absorption of fats and vitamins. Carboxylic acids are known for being able to hydrogen bond. In fact, many carboxylic acids, when interacting with each other, will form hydrogen bond donors, as shown on this slide here. So the carbonyl of one carboxylic acid will accept a hydrogen bond from the OH group of another carboxylic acid. And then the hydroxyl group of the left carboxylic acid will hydrogen bond or donate a hydrogen bond to the carbonyl of the other carboxylic acid. As a result of hydrogen bonding, carboxylic acids tend to have very high boiling points. In fact, they have higher boiling points than alcohols of similar size. Here's a comparison between acetic acid and propanol. You can see that acetic acid has a higher boiling point. Both alcohols, or at least this example of an alcohol and carboxylic acid, are completely water soluble. But in general, carboxylic acids will be slightly more water soluble than alcohols. Nitriles will interact with other nitriles through London forces as well as dipole-dipole interactions. Nitriles are not capable of donating a hydrogen bond, but they can accept a hydrogen bond. Here is an example of how two nitrile molecules will interact with each other. One carbon of, or the carbon of one nitrile will have a partial positive charge, so it aligns with the nitrogen of a second nitrile molecule. And so this leads to a dipole-dipole interaction. As a result of these dipole-dipole interactions, nitriles will have um, uh, a boiling point in water solubility a little bit higher than, let's say, alkanes, but they generally will have lower boiling points, lower water solubility than alcohols and carboxylic acids, which are capable of hydrogen bonding. Carboxylic acids, as the name implies, are considered acids or an acidic functional group. This is due to the fact that the conjugate base of a carboxylic acid will be resonance stabilized. So here's an example with acetic acid, which has a pKa of about 5. When treated with base, it produces a conjugate base that has a negative charge. That negative charge will be resonance stabilized between two oxygens. Compare that to an alcohol like ethanol, which has a pKa of roughly about 16. When treated with base, it produces a conjugate base, which is not residence stabilized. So that explains why carboxylic acids are more acidic than most functional groups, including alcohols. Carboxylic acids, like other acidic functional groups, are affected by electron withdrawing groups and electron donating groups. For example, here we have acetic acid, which has a pKa just slightly under 5. If we add an electron donating group, like a methyl group, notice the pKa increases, which means the molecule is less acidic. With halogens, which are electron withdrawing groups, the pKa generally decreases, and it decreases based on electronegativity. So the more electronegative groups would make the carboxylic acid more acidic. This is a result of these halogens withdrawing electron density from the proton. So in the case of a fluorine, because it's a highly electronegative atom, it will place a high partial positive charge on the hydrogen of the carboxylic acid, which will make it want to react more like an acid. Another way of looking at it is if we take a look at the conjugate base of one of these carboxylic acids. So after we remove the proton, we're going to have a negative charge on the oxygen. And having an electron withdrawing group, for example, here a fluorine, would mean that that negative charge would be stabilized more so than without the electron withdrawing group. The same thing or the opposite situation would occur if we have an electron donating group, which would destabilize this negative charge and make the conjugate base less stable, less likely to form, and therefore the acid would be less acidic in that case. Generally, the further away the electron withdrawing group or electron donating group is from the carboxylic acid, the less of an effect it has on the acidity. As an example, chlorine, which is an electron withdrawing group, if it's right next to the carboxylic acid, it lowers the pKa quite a bit. So it lowers it from 4.82 to 2.86 in this example. As we move that chlorine further and further away, notice the pKa starts to increase and essentially goes back to pretty close to 4.82. This is a result of the chlorine having less of an effect the further it is away from the acidic functional group. If we compare the acidity of a typical carboxylic acid on an alkyl group versus an aryl group, generally the aromatic ring will make the carboxylic acid more acidic than, let's say, a methyl group. One way of thinking about this is the hybridization of the carbon right next to the carboxylic acid. So in the case of benzoic acid, the pK is about 419, and we have a carbon that is sp2 hybridized. In the case of acetic acid, the pK is about 476, and the carbon next to the carboxylic acid is sp3 hybridized. We consider sp2 hybridized atoms if everything else is the same, more electronegative than sp3 hybridized atoms. So carbon, when it's sp2, is more electronegative than when it's sp3. One way of thinking about this is an s orbital is closer, or the electrons in an s orbital are closer to the nucleus because of the spherical shape, compared to the electrons in a p orbital, which are a dumbbell shape. So if a carbon has more s character, meaning a higher percentage of an s orbital, generally those electrons will be closer to the nucleus, and therefore we consider that atom more electronegative. When we add substituents around a benzoic acid, similar to substituents on an alkyl carboxylic acid, we can affect acidity. So electron withdrawing groups like halogens would generally make a carboxylic acid more acidic. when we add electron donating groups like alkyl groups, those groups will make the carboxylic acid less acidic due to electron donation. Here's an example with fluorine when it's ortho, meaning at the carbon right next to the carboxylic acid. So that would be this one here or this one here. The pKa is lower, so 3.3 compared to 419 without that substituent. When we move it to the meta position, it's slightly higher, so it starts to go back to 419 as we move further and further away from the carboxylic acid. And then the para position, if we put a fluorine at the para position here, the pKa is 4.1, so fairly close to benzoic acid. This effect that we're seeing here is called an inductive effect. So an inductive effect or induction is basically withdrawing electron density or donating electron density due to electronegativity differences. And this is typically done through bonds as well as through space. Some groups, like a nitro group, are electron withdrawing or electron donating, not only through induction, but also through resonance. As an example, when we have the nitro group at the ortho position, the pK is about 2.2. When it's at the meta position, it's 3.5. So this so far matches pretty well to what we saw with inductive withdrawing groups like the halogens, like fluorine. But notice in this case, when we place the nitro group at the para position, the pK is actually slightly lower than when it is at the meta position. So it's actually more acidic when it's at the para position. The way we can explain this is due to resonance. So if we look at the resonance structure below, we can explain this example. So with the para-substituted benzoic acid, we can move electron density away from the carboxylic acid and have a structure that has a positive charge right next to the carboxylic acid. That positive charge behaves like an electron withdrawing group, and it makes this hydrogen on the carboxylic acid more acidic. When we place the nitro group right next door to the carboxylic acid, the nitro group will, in one resonance structures, have a positive charge right next to the carboxylic acid. This positive charge, similar to what we saw with the para-substituted nitro-benzoic acid compound, will have an electron withdrawing effect on the carboxylic acid. It will make this hydrogen more acidic as a result. When we have a meta-substituted nitrobenzoic acid, if we try to draw other resonance structures, for example, this one here, we will have the positive charge always further away from the carboxylic acid than we did when we have an ortho or a para-substituted nitrobenzoic acid. If we try to draw other resonance structures, the closest we can get this positive charge will be either at this carbon or this carbon. And so it will never get as close to the carboxylic acids as we saw with the ortho substituted nitro compound. And so this explains why having a meta substituted nitrobenzoic acid, we don't have we don't have a compound that is as acidic as the para substituted example. Look at a few more examples of substituted benzoic acids. So the pKa of benzoic acid, as we mentioned previously, is 4.19. If we add a methyl group at the para position, it goes up to 4.38. So we can explain this by the fact that the methyl group and other alkyl groups are electron donating through induction. We have now three other examples or substituents in this slide here. So we have a methoxy group, which it leads to a pKa of 4.46 when it is at the para position of benzoic acid. A phenol or hydroxy group, it leads to an increase of the pKa value, and the amino group also does the same thing. So notice that the methoxy, the hydroxy, and the amino group are all making benzoic acid less acidic, not only than when it doesn't have any substituents, but also even when it has a methyl, which is an electron donating group. So how do we explain this? So we believe that these groups are electron withdrawing through induction. As you would expect, a highly electronegative atom like oxygen or nitrogen would make the carboxylic acid slightly less acidic, more acidic because of electron withdrawing through induction. However, how do we explain these values here? So it turns out that resonance has a bigger role. It is making benzoic acid less acidic through resonance. So what's common about these three substituents is that they all possess lone pairs on these atoms, so whether it's oxygen or nitrogen, and that lone pair is right next to the ring. So using this hydroxy substituted benzoic acid as an example, we can use the lone pairs on this oxygen to push electrons towards the carboxylic acid, and we could come up with a resonance structure that has this negative charge right next to the carboxylic acid. That negative charge behaves as an electron donating group, and it makes this hydrogen of the carboxylic acid less acidic. When the hydroxy group is ortho to a carboxylic acid, we can draw another resonance structure as shown here, where we push electron density towards this carbon right next to the carboxylic acid. That places a negative charge there, and that negative charge acts as an electron donating group, which will destabilize the conjugate base of this carboxylic acid, making it less acidic than if we did not have that ortho hydroxy group. When the hydroxy group is meta to the carboxylic acid, if we try to draw another resonance structure as shown here, so using this lone pair pushing electrons towards this carbon, we can place a negative charge there. That negative charge also acts as an electron donating group, but because it's not as close to the carboxylic acid as this negative charge when the hydroxy group is ortho or when it's para, as we saw on a previous slide, the negative charge here is not going to have as strong of an effect as an electron donating group. And so this compound here would be slightly or actually a little bit more acidic than the ortho substituted hydroxy compound and the para substituted hydroxy compound. This table here summarizes nicely how different substituents affect the acidity of benzoic acid. The first three examples, the nitro group, the nitrile or the cyano group, and an aldehyde, generally will make a carboxylic acid more acidic, not only through induction, but also through resonance. And this is especially true when the groups are ortho and para. The next two, the bromine and the chlorine, are electron withdrawing groups, mostly through induction. And so the pattern follows that as the group gets closer to the carboxylic acid, the more of an effect it has. And so the further it is, the less of an effect it has. Methyl group here, as we talked about before, is an electron donating group through induction. And then the last three groups here, the methoxy, the hydroxyl group, and the amino group, are all electron donating, not mostly through resonance, but they are slightly electron withdrawing through induction. But overall, for the most part, they behave as electron donating groups because of the strong effect of resonance. And again, this is especially true when they're ortho and para. Nitriles are generally more acidic than alkanes, and this is due to the fact that the nitrile group can resonance stabilize a negative charge next to the nitrile group. Here's a couple examples. Starting off with a nitrile, typical pKa for nitrile like acetonitrile, which is shown here, is around 25. A typical alkane is anywhere between 50 to 60 pKa units. If a base deprotonates a nitrile, we have this carbanion that is shown here. The same thing would happen with an alkane. However, in the case of a nitrile, we can resonance stabilize that negative charge as shown, where the electron density can move into or towards the nitrogen to create this stabilized conjugate base. Since the conjugate base is stabilized, that means that acid is going to be more acidic as the pKa show. In this question, we will rank the following three compounds in order of increase in acidity, starting from the compound that is least acidic. In a question like this, where we have to rank compounds in order of increase in acidity, we want to find what the differences are between the three compounds. In this case, we basically have three benzoic acid compounds with three different substituents at the para position. Benzoic acid has a hydrogen, then we have a 4-methyl substituent in one of the compounds, and then a 4-chloral substituent in the last compound. Methyl groups are generally electron donating and they will make benzoic acid less acidic. A chlorine is generally electron withdrawing and it will make benzoic acid more acidic. Therefore, the 4-methyl substituted benzoic acid would be the least acidic, followed by benzoic acid, and then lastly, the most acidic compound is the 4-chloral substituted benzoic acid. In naming carboxylic acids, we always follow the same rules that we have done so far with naming other functional groups, in that we want to make sure that the parent chain has the principal functional group, in this case the carboxylic acid. In naming the compound, we want to use the suffix oic acid or dioic acid if we have two carboxylic acids. Here's a very simple example having 3 carbons and a carboxylic acid. So this would be named as propanoic acid. The next example has 5 carbons in the parent chain, which has also the carboxylic acid. So this compound is named as a pentanoic acid with a substituent on carbon 4, a methyl substituent. Note that this is carbon 4 since the carboxylic acid is at the right side of the molecule. It is at the beginning of the chain, so we start from there and we get to where the methyl group is, which is carbon 4. So this compound is named as a 4-methyl pentanoic acid. In the next example, we have 8 carbons in the chain that contains both carboxylic acids. So this compound, at least the parent name for it, is octane dioic acid. It has 2 substituents. Normally, we would want to start from the side that has the parent or the main functional group. In this case, there's 2 carboxylic acids. So the next rule that we will want to follow in order to determine how we number the substituents is based on which substituents are closer to one side or the other. In this case, both substituents are the same distance from the right or the left side of the chain. So they are on the 3rd carbon from the right for the methyl group, and the ethyl group is on the 3rd carbon from the left. So the last sort of tiebreaker rule is alphabetical order of the substituent. So an ethyl alphabetically goes first. So we are going to number that carbon 3. So it's 3-ethyl, 6-methyl. Lastly, There are many common names we use for carboxylic acids, probably more than most other functional groups. Here are three that you should definitely try to remember. Formic acid has one carbon, acetic acid has two, and benzoic acid has this benzene ring plus the carboxylic acid. This table summarizes many common names for carboxylic acids. You do not need to remember these. We previously talked about trying to memorize formic acid, acetic acid, and benzoic acid. Those are the three that you should remember. The rest of these, you're going to come across them occasionally. It will be just as easy to look them up. So you do not need to memorize them. But I wanted to show you some of them. As you go through the course, you'll see a few of them come up. Nitriles are named with the suffix nitrile. Other than that, we typically give the alkane name followed by the word or the suffix nitrile. Here's an example. This one has 5 carbons, including the nitrile. Note that we do count the carbon of the nitrile. The nitrile is on the right side, so that's where we're going to start numbering this compound. And then when we get to carbon 4, we have a methyl group. So this compound is named as 4-methyl pentane nitrile. The next example has a nitrile. So that would be carbon 1. Then carbon 2 here, 3, 4, 5, and 6. So there is a total of 6 carbons in the longest chain that has the nitrile and also has this double bond functional group. So this compound is named as hex 3-ene, 3 because that's where the double bond starts. The double bond starts on the 3rd carbon if we start counting from the nitrile. And then the last part of the name would be nitrile. We also have a substituent on carbon 5 and also another one on carbon 2. They're both methyl groups. And so we add those substituents in front of the parent name and name it as 2,5-dimethyl hex 3-ene nitrile. Lastly, you look for any stereochemistry. We do have stereochemistry around the double bond. It is E stereochemistry, and so we add that in front of the name. This double bond has E stereochemistry based on the fact that this carbon chain is on the opposite side as this one towards carbon 5, and so that's why we name it as E. Occasionally, we might need to give the nitrile as a substituent in naming a compound. So for example, a carboxylic acid has a higher priority, it's a higher priority group than a nitrile. And so any compound that has a nitrile and a carboxylic acid, the nitrile will be named as a substituent. Here's an example. This compound has 7 carbons in the longest chain containing the carboxylic acid. And so we would name this as a heptanoic acid. We have a substituent on carbon 3, which is a cyanyl group, and another substituent on carbon 6, which is a 6-fluoro substituent. Common names that you should try to remember for nitriles is acetonitrile, which has these 2 carbons, and benzonitrile, which has a benzene ring attached to a nitrile group. In this question, we're going to try to name this compound. It has a carboxylic acid. It has 1, 2, 3, 4 carbons in the longest chain, and it has a methyl substituent. Has 4 carbons and a carboxylic acid. So we would name this as butanoic acid. It has a methyl group on carbon 3, so it is 3-methyl butanoic acid. We're now going to jump into the reactions of preparing carboxylic acids, and we're going to start off with reactions that we are already familiar with. So for example, we can oxidize primary alcohols and aldehydes into carboxylic acids using chromic acid, as shown here. So primary alcohol in the first example using chromic acid, which can come from either using chromium trioxide as shown in this example, or sodium dichromate, which is a reagent we have used in the past with sulfuric acid and water to make chromic acid as well. That primary alcohol will be oxidized to a carboxylic acid. Note that this reaction goes through an aldehyde, which then gets oxidized to a carboxylic acid. If we start off with an aldehyde, we can do the same reaction to make a carboxylic acid. Another method used to make carboxylic acids is the oxidation of the side chain of aromatic compounds. This can usually be done with strong oxidizing agents such as chromic acid or potassium permanganate. Here is an example. This benzene with an ethyl side group can be oxidized with chromic acid, whether we use chromium trioxide or sodium dichromate. We would mix it with sulfuric acid and water and heat it, usually around 100 degrees or more. That ethyl group will be turned into a carboxylic acid. Here's another example containing a methyl group, a propyl group, and a terbutyl group. Note that in this example, only the methyl group and the propyl group are converted into carboxylic acids. The terbutyl group is not. What we learn from examples like these is that in order to do an oxidation of the side alkyl group of an aromatic ring is that a benzylic hydrogen is required. In other words, here's the benzylic carbon. We must have a hydrogen, at least one hydrogen at that position. So if we have an ethyl group, that can be converted into a carboxylic acid. If we have a methyl group or a propyl group. In the case of a terbutyl group, that carbon only has bonds to other carbons. It does not have a hydrogen, and therefore it cannot be oxidized. It is believed that under this oxidation, a hydrogen, a benzylic hydrogen, is abstracted and converted into a radical, which starts the reaction. Note that no matter what the size of the chain is, it will always be converted into a carboxylic acid. So we can have a very long alkyl group, and it will still be converted into a carboxylic acid. Potassium permanganate is a strong oxidizing agent that if we heat an alkyl group on a benzene compound to around 100 degrees Celsius, we can oxidize that side group into a carboxylic acid. So for example, a methyl group can be oxidized into a carboxylic acid. Similar to the oxidation with chromic acid of the side groups of aromatic compounds, we must have a benzylic hydrogen on that carbon next to the benzene ring. Otherwise, the oxidation does not occur. So to make carboxylic acids is by using a Grignard or organolithium reagent with dry ice. Here's a couple of examples. If we have an alkyl halide and we add magnesium or lithium, we can make the Grignard reagent or an organolithium reagent. And then if we add CO2 or dry ice, which is the solid form of CO2, we can then make a carboxylic acid out of that Grignard or organolithium. Note that the product from this reaction will have the same number of carbons as the Grignard or organolithium reagent, plus one more that comes from the CO2 molecule. So in this example, we have 4 carbons in the Grignard reagent, 4 carbons in the organolithium reagent. If we get one more from CO2, we will have a carboxylic acid that has 5 total carbons. The next example is a phenyl Grignard reagent that is mixed with CO2 followed by aqueous acid to make benzoic acid. Here's a look at that mechanism. So a Grignard reagent will add to the carbon of CO2. So think of this as a carbanion adding to the slightly positively charged carbon of CO2, similar to the reaction of Grignard reagents with a carbonyl of a ketone or an aldehyde. That will lead to breaking one of these double bonds to create the carboxylate ion that you see here. And then lastly, if we add aqueous acid, we can protonate that oxygen to make benzoic acid. Here's one more example with an alkyl halide. If we add magnesium or lithium, we can make a Grignard or an organolithium from it. Then if we add CO2, we can add a carboxylic acid. And note that we had to add aqueous acid at the end to turn the carboxylate ion into a carboxylic acid. Notice the product will have an extra carbon from the CO2. So we originally started with a cyclopentane. We're going to add the carboxylic acid on the outside. And we're adding essentially one more carbon because of the CO2. In this reaction, we're going to give the missing reagents from the following reaction. We're starting off with an alkyl halide, and we're converting it into a carboxylic acid. Notice that the carboxylic acid has an extra carbon compared to the original alkyl halide. This reaction is set up to be a carboxylation of an organolithium or a Grignard reagent. So if we start off with an alkyl halide, if we add magnesium or lithium, we could convert it into a Grignard or an organolithium. And then if we add CO2, we can add a carboxylic acid where that chlorine is. And so the reagents that are missing are magnesium or lithium, followed by CO2, followed by aqueous acid. One of the reasons why nitriles are in the same chapter as carboxylic acids is because nitriles are very easily converted into carboxylic acids by hydrolysis. If we heat a nitrile with acid or base, we can turn them into carboxylic acids pretty easily. Here's an example of a base catalyzed hydrolysis of a nitrile. So if we start off with a nitrile and we add sodium hydroxide, water, and heat, and then in a second step we add aqueous acid, we convert it into a carboxylic acid plus ammonia as a byproduct. The reaction starts by the sodium hydroxide, the hydroxide in particular, which is a strong base or a strong nucleophile, adding to the carbon of the nitrile, breaking one of the pi bonds to create this intermediate. That nitrogen has a negative charge, which will then be protonated by water, creating this intermediate. The intermediate will tautomerize into an amide. So notice the double bond is between the carbon and nitrogen, and there's a single bond to an oxygen. And then in the product of this tautomerization, we exchange the double bond, and now it is now between the carbon and oxygen, and there's a single bond to the nitrogen. As a reminder, tautomerizations are the rapid interconversion of constitutional isomers. So the two compounds you see here at the bottom of the slide are tautomers of each other. The next step, or the second half of this reaction, is essentially the hydrolysis of an amide. We're going to see this again in more detail in the next chapter, chapter 21. But here is how the reaction occurs. Sodium hydroxide, the OH in particular, will attack the carbon of the carbonyl, break the double bond to create a tetrahedral intermediate. And then that tetrahedral intermediate will break down to eliminate the amino group. So the oxygen will reform the carbonyl, eliminate the NH2. The product from that will initially be a carboxylic acid as shown here, but because this reaction is done under basic conditions, so sodium hydroxide is present in the reaction, it will deprotonate this acidic hydrogen of the carboxylic acid. For that reason, we have to use aqueous acid in a second step to neutralize that sodium hydroxide and convert the carboxylate ion into carboxylic acid. So any reaction that leads to making a carboxylic acid that is done under basic conditions, we always have to use a second step where we add acid to convert it into a carboxylic acid. Here's a look at how we can convert an alkyl halide into a carboxylic acid in a two-step sequence. I'm going to use the example of the synthesis of ibuprofen to illustrate this point. So if we start off with an alkyl halide, usually we need to use a primary or a secondary alkyl halide. If we add a cyano group, which is a good nucleophile, we can do an SN2 reaction and convert it into this nitrile here. Then if we hydrolyze the nitrile under basic conditions, we can convert it into a carboxylic acid. So we can go from an alkyl halide to a carboxylic acid through a sequence like this by first adding a cyano group and then hydrolyzing that cyano group. Nitriles can also be hydrolyzed under acidic conditions. So for example, acetonitrile, when mixed with sulfuric acid, water, and heated, will be converted into acetic acid plus ammonia. The reaction starts by protonating the nitrile nitrogen with sulfuric acid. We could also use the hydronium ion in this step. Then water, which is a poor nucleophile, will add to the carbon of the nitrile. That leads us to this intermediate. The water has now a positive charge, and so we'll use a base like the conjugate base of sulfuric acid. We could also use a water molecule to remove a proton from the water that just added and also get rid of the positive charge on the oxygen. That leads us to this intermediate, which tautomerizes to an amide, as we saw in the base catalyzed hydrolysis of nitriles. The second half of this mechanism is a hydrolysis of an amide under acidic conditions. We'll look at this again in a later chapter, but for now, we'll take a quick look at how this reaction occurs. It starts off with the amide oxygen on the carbonyl being protonated by sulfuric acid. Again, this can be done with the hydronium ion. That leads us to this intermediate, which gets attacked by water. The carbonyl is broken. We get now to a tetrahedral intermediate. A water molecule or the conjugate base of sulfuric acid can remove this proton, form a carbonyl here by eliminating the amino group. That leads us to a protonated carboxylic acid, which then loses a proton by using the conjugate base of sulfuric acid or another water molecule. And if we remove that proton, we will have now the carboxylic acid. In this question, we want to prepare phenylacetic acid, whose structure is shown here, from benzobromide. There are two methods we can use to go from benzobromide to phenylacetic acid. In both cases, we have to use a combination of reactions that we learned about. For example, we can add sodium cyanide to benzobromide to do an SN2 reaction and obtain this nitrile that you see here. Then we can hydrolyze that nitrile either under acidic conditions as shown here. By the way, we would need to heat this reaction. We can also do it under basic conditions, so sodium hydroxide water, and heat will do the same thing. And we could obtain from that phenylacetic acid. A second strategy we can use to go from benzoyl bromide to phenylacetic acid is by using a Grignard reagent or an organolithium reagent. So if we add magnesium or lithium, we can get this benzoyl Grignard reagent, or we can make a similar organolithium reagent if we use lithium as our metal. That carbanion can then add to CO2 followed by aqueous acid to make phenylacetic acid. Natural fatty acids generally have an even number of carbons. Generally, the chains are unbranched and they contain between 12 and 20 carbons. They're found in animal fats, vegetable oils, as well as biological membranes. Saturated fatty acids typically have only carbon-carbon single bonds. Unsaturated fatty acids will contain carbon-carbon double bonds. And natural unsaturated fatty acids typically have cis stereochemistry. Saturated fatty acids are solids at room temperature due to the strong London forces. If two saturated fatty acids align next to each other, you can clearly see that due to their own saturation, they can pack really well, which leads to very strong London forces as a result of the long carbon chains. Stereochemistry of the double bonds of unsaturated fatty acids prevent efficient molecular packing. As a result, the London forces between two unsaturated fatty acids is much weaker than compared to a saturated fatty acid. This leads to generally the melting point being below room temperature, which means unsaturated fatty acids are generally liquids or oils at room temperature. Trans fatty acids are unnatural fatty acids that result from a partial hydrogenation of unsaturated fatty acids. So in the food industry, sometimes food companies will hydrogenate the double bonds in an unsaturated fatty acid in order to produce a unsaturated fat. Sometimes this hydrogenation goes incomplete, and some of the cis double bonds are converted to trans double bonds. Trans fatty acids are unnatural and therefore unhealthy for humans. Omega-3 fatty acids are polyunsaturated fatty acids that contain a double bond on the third carbon from the opposite end of the carboxylic acid. These are generally found in fish, such as salmon, and they tend to be very healthy. At the bottom of the slide, you see an example of an omega-3 fatty acid. As you can see, there is a double bond starting on carbon 18. That is what makes it an omega-3 fatty acid. The melting point of saturated fatty acids generally increases with the increasing number of carbons. You can see on this table that lauric acid, which has a total of 12 carbons, has a melting point of 45 degrees Celsius. Compare that to myristic acid, which has 14 carbons and therefore has a melting point slightly higher of 55 degrees Celsius. Note that the melting point of all of the saturated fatty acids shown on this table are all above room temperature, and as a result, they tend to be solids at room temperature. Unsaturated fatty acids generally have lower melting points than saturated fatty acids with a similar molecular weight. For example, oleic acid, which has 18 carbons, has a melting point of around 13 degrees Celsius. This is, notice, lower than room temperature, which is roughly about 25 degrees Celsius. And as a result, oleic acid, like most unsaturated fatty acids, are liquids at room temperature. Compare oleic acid to stearic acid, which is a saturated fatty acid with 18 carbons, which has a melting point of around 69 degrees Celsius. And as a result, stearic acid is a solid at room temperature. Linoleic acid, like many unsaturated fatty acids, are considered essential fatty acids since they are required for normal body function but must be obtained from the diet. This is a result of the fact that mammals lack an enzyme that introduces a double bond beyond carbon 9 in fatty acids. Omega-3 fatty acids such as linoleic acid are in cell membranes of the heart and are important in stabilizing the heart rhythm. An important function of fatty acids is the fact that they are components of the lipid bilayer in cell membranes. The lipid bilayer of cell membranes is composed of a glycerol unit, which is a triol. It also contains ester bonds between fatty acids and some of the alcohols on glycerol. It contains a phosphoric acid unit as well as an amino alcohol unit. Saturated fatty acids and cholesterol generally make the lipid bilayer more rigid or less fluid, while unsaturated fatty acids will make it less rigid. Discuss the preparation of nitriles. We'll start with a reaction we have seen before, which is the substitution of an alkyl halide by a cyanonucleophile. As shown here, if we use benzyl bromide, we can do a substitution with sodium cyanide. Simple SN2 reaction will lead us to producing a nitrile product. Similarly, if we use a secondary alkyl halide, we can do a substitution with sodium cyanide. In this case, since it is an SN2 reaction, we will see an inversion of stereochemistry. Let's now take a look at the reactions of nitriles. Before we look at specific examples, let's go back to the nucleophilic addition of nucleophiles to carbonyl compounds such as a ketone. Generally, in nucleophilic addition reactions, the nucleophile will add to the carbon of a ketone, break the double bond to form an alkoxide or tetrahedral intermediate, and then depending on the reaction conditions, we will either protonate this oxygen with acid, or this nucleophile will push out the oxygen and form an imine or some sort of imine derivative. In the cases of nitriles, we can see, at least initially, a similar reaction where the nucleophile will add to the the carbon of the nitrile, break the triple bond of the nitrile, form an imine ion, and then depending on, again, the exact reaction, we will get different products from this. Nitriles are a diverse functional group that can be hydrolyzed into amides and then carboxylic acids. They can also be reduced using hydrogenation conditions or a hydride reagent such as lithium aluminum hydride and be converted into an amine. Or nitriles can react with a Grignard to form a ketone after hydrolysis of the intermediate. Nitriles can be converted to carboxylic acids under aqueous, acidic, or basic conditions. The reaction goes through an amide intermediate, which is further hydrolyzed to the carboxylic acid. Here's a specific example using this nitrile. If we heat it with water, sodium hydroxide, and then we follow the reaction with aqueous acid, we can obtain a carboxylic acid. We can do the same reaction with sulfuric acid, water, and heat to produce a carboxylic acid. Note that in the basic hydrolysis, because the reaction leads to a carboxylic acid, which is an acidic functional group, we must use a second step where we add aqueous acid to neutralize the base and also to convert the conjugate base of the carboxylic acid into the carboxylic acid. Under acidic conditions, when we do the hydrolysis, there is no need for a second step since the reaction yields the carboxylic acid directly. Nitriles can be converted into amines by using a hydride reagent such as lithium aluminum hydride. As an example, this nitrile here, when treated with lithium aluminum hydride, will be converted into this primary amine. Notice that the amine has the same number of carbons as the nitrile that we started with. So there are 1, 2, 3, 4 carbons in the longest chain, plus a methyl group on the second carbon. In the case of the nitrile, we also have 1, 2, 3, 4 carbons, and there is a methyl group on the second carbon. If we use benzonitrile, we can reduce it into this primary amine as well with lithium aluminum hydride. The reaction starts by lithium aluminum hydride providing a hydride, so an H minus, which will add to the carbon of the nitrile, break the double bond or the triple bond, excuse me. That leads us to this iminium anion intermediate that we see here. This can be further reduced but with another equivalent of lithium aluminum hydride to add another hydride to the carbon of the nitrile, what used to be the nitrile, and obtain this oddly looking intermediate with a -2 charge. This will sit around until we finish the reaction and add water or aqueous acid at the end of the reaction to give us the corresponding amine, which in this case is benzolamine. DIBA is a hydride reagent which we saw earlier this semester, which is used to convert esters into aldehydes. Another use for DIBA is we can convert a nitrile into an aldehyde. Here's an example using this nitrile. If we use DIBA followed by aqueous acid, we can convert it into this aldehyde. Note that the aldehyde has the same number of carbons as the nitrile. So in the case of the nitrile, there are 1, 2, 3, and 4 carbons in the longest chain. And in the aldehyde, there's also 4 carbons in the longest chain. There's also a methyl group in the second carbon in both the reactant and in the product. A byproduct of the reaction will always be ammonia in this reduction. Here's a second example, including the mechanism for the reaction. So benzonitrile, when we treat it with DIBA, it's first going to lead to a coordination between the nitrogen of the nitrile and the aluminum of DIBA. Note that DIBA has 3 groups around the aluminum, so 2 isobutyl groups and a hydrogen. And so it is a good Lewis acid, which can coordinate to the lone pairs on a nitrogen. Once this coordination occurs, or this Lewis acid base reaction occurs, we obtain this intermediate, which has a bond between the nitrogen and the aluminum. It has a formal positive charge on the nitrogen, has a formal negative charge on the aluminum. And this intermediate now has an aluminum that, because of the 4 groups that it has bound to it, the hydrogen on the aluminum is now considered a hydride. So this hydrogen or hydride will add to the carbon of the nitrile, lead to breaking one of the pi bonds in the nitrile, and lead us to this intermediate, which is essentially an imine anion. This intermediate will now be protonated, so the nitrogen here, which really has a negative charge on it, will attack this water or aqueous acid, and be protonated and turn into an imine. As we learned earlier this semester, imines, when treated with aqueous acid, will be converted into the corresponding carbonyl, either an aldehyde or a ketone, depending on the structure of the imine. In this case, this imine will be converted into this aldehyde shown here, benzaldehyde, plus ammonia. Nitriles can also be reduced with hydrogenation. So here's an example with a nitrile. If we use a high pressure of hydrogen, so 100 atmosphere of hydrogen, and nickel catalyst, we can reduce this nitrile into the corresponding primary amine. There's a second example here with another nitrile. Again, under the same conditions, we can reduce it to a primary amine. The high pressure hydrogen here can be achieved by doing the reaction in a stainless steel reactor and pumping it with hydrogen gas while the reactants are also present. If we add a Grignard reagent or an organolithium reagent to a nitrile, we can convert them into ketones that have an alkyl group matching the nucleophile. As an example, if we have this nitrile here and add an ethyl Grignard reagent, we can transfer this ethyl group to the carbon of the nitrile, and then the corresponding double bond between carbon and nitrogen will eventually be hydrolyzed into a ketone. There will also be a byproduct of ammonia. Here's a look at another example and the mechanism involved. If we use methyl Grignard, the carbanion here, the methyl group, will add to the carbon of the nitrile, break one of the pi bonds of the nitrile, leading to this imine anion, which will be protonated by aqueous acid to give us initially an imine. And as we learned earlier this semester, imines, whenever we add aqueous acid, can go back to the corresponding carbonyl, usually a ketone or an aldehyde. In this case, this imine will be converted into this ketone plus ammonia as a byproduct. Example using benzonitrile. If we add ethyl Grignard, the ethyl group will be added to the carbon of the nitrile, and then the nitrile will be initially turned into an imine anion, and then that imine anion will react with aqueous acid to first turn into an imine, which will be then hydrolyzed into this carbonyl shown in the product. The compound shown on this slide, called linomarine, is a compound that is produced by several plants, including cassava, and is used as a way to generate hydrogen cyanide when these plants have the need to defend themselves. So through a reversible reaction we learned earlier this semester, this oxygen can form a carbonyl by eliminating the cyanide group, which eventually will be protonated and produce hydrogen cyanide. In this question, we're going to try to synthesize the following alcohol, starting with this alkyl halide. Note that the alkyl halide has one less carbon, as well as, of course, a different functional group than the alcohol shown as a product. In this transformation, we're converting an alkyl halide into an alcohol, and in the process, we're also adding a CH2 group. Now, you might recall that alcohols will usually, or one way of making alcohols would be by reducing a carboxylic acid. And so if we can somehow add a carboxylic acid from the alkyl halide, we can complete this synthesis. As we learn in this chapter, there are two ways that we can convert an alkyl halide into a carboxylic acid. So one way would be by adding magnesium or lithium to convert this halogen into a metal bond. So we can create a corresponding Grignard reagent, which can then add to CO2, which is dry ice. And then if we add aqueous acid, we can end up with a carboxylic acid shown here. We could do a similar reaction by using sodium cyanide to do an SN2 reaction on this alkyl halide and add a nitrile group. And then if we hydrolyze that nitrile group, either under acidic condition as shown here, or under basic conditions, we can convert it into a carboxylic acid. If we then reduce this carboxylic acid with lithium aluminum hydride, we can obtain the corresponding alcohol. Notice the alcohol will have the same number of carbons as the carboxylic acid. The carbon that we added, or the extra carbon we added in this carboxylic acid, will come from either CO2 or from the cyanide nucleophile. In this question, we want to make the following ketone from a nitrile. One of the reactions that we learned about in this chapter is that we can take a nitrile and add a Grignard reagent to convert it into a ketone. The Grignard reagent will generally add an alkyl group to the carbon of the nitrile. And so in this case, we're adding an ethyl group. And then we will initially obtain a nitrogen double bond. So the nitrile here will be converted into an imine anion. This carbon will have an ethyl group from the Grignard reagent, and it will have an ethyl group from the nitrile that we started with. So here's an ethyl group, so that could be that one. And then we could add an ethyl group from the Grignard reagent. That anion here will be protonated by water in the last step of the reaction. And then the resulting imine will be eventually hydrolyzed into this ketone. Let's review some of the reactions we learned about in this chapter by looking at some of these examples. In the first reaction, we're going to take an organolithium and add CO2 followed by aqueous acid. In the second reaction, we're going to use a nitrile and we're going to add sodium hydroxide, water, and heat, which are basic hydrolysis conditions, followed by aqueous acid. Or we can add sulfuric acid, water, and heat. If we start off with a primary alcohol or an aldehyde, we can do an oxidation reaction with chromic acid, and that could involve either chromium trioxide or sodium dichromate. If we have a benzene compound that has an alkyl group, we can oxidize this compound with chromic acid as well. Note that we can also do this reaction with potassium permanganate. In the last reaction here, we're going to take an alkyl halide and we're going to add sodium cyanide. Adding CO2 to an organolithium or even a Grignard reagent will lead to adding a carboxylic acid to the carbon where the metal is. By adding aqueous acid in the second step, we will make sure that the oxygen is protonated, giving us the carboxylic acid. If we take a nitrile and we add sodium hydroxide, water, and heat, we will hydrolyze this nitrile into the conjugate base of a carboxylic acid. So that means this product here, minus the hydrogen with a negative charge on the oxygen, will be produced. So this results from the fact that the reaction is done under basic conditions. If we add aqueous acid, the conjugate base of this compound will be converted into the carboxylic acid you see here. We can do the same reaction just by simply using sulfuric acid, water, and heat, and so a nitrile will be hydrolyzed to this carboxylic acid. So note that whenever we do reactions with or that produce a carboxylic acid under basic conditions, and so we saw that with the first reaction on top, and at least the first part of this reaction. By doing it under basic conditions, we always first obtain the conjugate base of a carboxylic acid, so we have to use a second step in both reactions to convert it to a carboxylic acid. Doing it under acidic conditions skips that step, and so we simply just go from the reactant to the carboxylic acid. With a primary alcohol or an aldehyde, we can oxidize it with chromic acid to convert it into the corresponding carboxylic acid. Notice both the aldehyde and the alcohol contain 3 carbons, so the product here will also contain 3 carbons. Whenever we have an aromatic compound with a side group, an alkyl group, that has at least one benzylic hydrogen, so in this case there is 1 hydrogen right here, that allows for the entire group, the alkyl group, to be converted into a carboxylic acid. And it doesn't matter that it is an isopropyl group, it could be a methyl group, it could be an ethyl group, just a straight propyl group, a butyl group, anything that has benzylic hydrogens can be converted into a carboxylic acid. In the last reaction here, we have an alkyl halide. If we add sodium cyanide, the cyano group will attack the carbon where the leaving group is and replace it. Since this is an SN2 reaction, it works best when it's a primary alkyl halide or even a secondary one. In the first reaction in this slide, we're using a nitrile and we're doing a hydrogenation. The next reaction involves a nitrile reacting with thiol followed by aqueous acid. The next reaction is a nitrile reacting with lithium aluminum hydride followed by aqueous acid. And then lastly, we're using a nitrile reacting with an organolithium or a Grignard followed by aqueous acid. We start off with a nitrile and we do hydrogenation. So usually for nitriles, it will be done with nickel and high pressure hydrogen. We can reduce the nitrile into a primary amine. Notice the amine will have the same number of carbons as the nitrile. If we take a nitrile and we add diol followed by aqueous acid, the carbon here where the nitrile is will be converted into an aldehyde. Although not shown in this example, we typically will also have a byproduct of ammonia, which is NH3. In the next reaction, we're starting off with a nitrile. If we add lithium aluminum hydride, we're going to reduce the nitrile similar to the hydrogenation reaction into a primary amine. And then lastly, if we take a nitrile and add a lithium reagent or a Grignard reagent, these carbanions will be transferred to the carbon of the nitrile. So in this case, we're adding a methyl group. And then the carbon to nitrogen triple bond will eventually be converted into a ketone as shown in the product. Notice the ketone has a methyl group on the right side. The left side is the same carbon chain that we see with the nitrile. Note that the carbon here that is part of the nitrile will be the carbon that is part of the ketone in the product. To finish this chapter, let's do a synthesis problem. So we're starting off with a primary alcohol and we're converted into a carboxylic acid. Notice that the carboxylic acid has 1 more carbon compared to the alcohol that we're starting with. In this case, we can answer this question. So One of the things we want to do though is first convert this alcohol into a good leaving group so that we can do substitution reactions. So for example, we can convert this alcohol into a tosylate by adding tosyl chloride and pyridine, which is a base. That will convert this alcohol into the tosylate that you see here. Remember, tosylates are similar to alkyl halides, so we can do substitution reactions. So for example, we'd add sodium cyanide, which will replace the tosylate group with a cyano group, as shown here. And then the nitrile can be hydrolyzed either under basic or acidic conditions. I chose to use the acidic conditions since they're usually simpler. And so the nitrile, we convert it into this carboxylic acid. Another way that we can make this synthesis complete is by converting the alcohol into an alkyl halide. So we could use PBr3, for example, to convert it into this bromide, or we could use sodium bromide to replace the tosylate in this compound into a bromide. Then the alkyl halide can be converted into a Grignard or an organolithium by adding magnesium or lithium. And then that turns these compounds into carbanions, which are nucleophilic, and they can react with CO2 to add a carboxylic acid. Note in this reaction, not only did we transform the alcohol into a carboxylic acid, but we also added an extra carbon, which we can do by adding the cyanide nucleophile if we go this route, or by adding CO2 by going through the Grignard or organolithium route.